Hey guys, it's Will here, and we're just starting on the solutions of all the problems from McQuarrie General Chemistry, starting with Chapter 1, which is going to be entitled Chemistry and the Scientific Method. And I will admit that this chapter is going to be a little bit abstract, but again, it's going to teach you a lot of really great concepts that you're going to use throughout your scientific career. So although it may seem abstract, there are many different things that you'll use over and over and over again if you continue to do science classes. Okay, first is going to be the scientific method. Obviously, that's how questions are asked, hypothesis is formed, etc., all the way to the metric system. So this first chapter is going to cover all that. We'll go over every single question. I'll walk you through all the questions, all the answers, and all the concepts, and then we'll start moving on to the more specific aspects of chemistry in the McQuarrie book. So with that said, let's go ahead and start with the first chapter and the first question at the end of the chapter. That's question 1-1. Okay, so first question of the first chapter of McQuarrie is, what is the difference between a hypothesis, a law, and a theory? Okay, so first things first, a hypothesis is going to be a proposition that is put forth as a possible explanation for or prediction of an observation or phenomenon. So the easiest example to use here is thinking about Isaac Newton, right? So he sees an apple fall down from a tree and he comes up with the theory of gravity, right? But the hypothesis is going to be there's some sort of force that pulls downward any object, that is on the earth. That's the hypothesis. And so the next part of the question, what is a law? A law is going to be a concise statement of a relationship among phenomena that are all under the same conditions, right? You're under this tree, all the apples are falling, okay? They're all subject to gravity. That's what a law is going to be. And throughout your study of chemistry, there's going to be many different laws. Law of thermodynamics, for example, heat capacity, etc., etc. They're going to go on and on. But basically, you have the same conditions, and under the same conditions, something predictable happens. That's what a law means under this definition. Okay, and last but not least is a theory. So a theory is going to be some sort of unifying principle. And that unifying principle is going to explain a law, and it's going to be based on experimental observations, right? Every time there's an apple that's released from the tree, it falls down. My theory is that there's a force called gravity that pulls things down, okay? That's what a theory is going to be. So again, unifying principle is going to explain a law, and it's going to be based on, importantly, experimental observations. All right, moving on to question 1-2. An experiment is performed that disproves a long-standing theory. According to the scientific method, how should the scientists involved proceed? Well, you should proceed by confirming the results of the experiment by, for example, repeating the experiment. And if the experiment's confirmed and the results hold up, you need to either revise the theory or discard the theory and come up with a new theory. Moving on to question 1-3. In the context of the scientific method, comment on the statement, the theory of evolution is a fact. And the answer is going to be that the theory of evolution is not quote-unquote an absolute fact in the context of the scientific method. Basically, it's a theory. When you're talking about the scientific method, all you have is theories. And some theories are much more robust than others, okay? And so for evolution, it's a theory with a lot of support, but no theory can be proved via experiment. The theory lasts until it's actually disproven. So it's kind of a negative thing. So essentially, if you put forward a theory and it's rock solid, you're waiting for someone to run an experiment that disproves that theory. And we're going to get to this a little bit later down the line, but the central dogma of molecular biology is actually one of those great theories that really illustrates this. That basically everyone thought for many years that things were one way, e.g., DNA, was basically translated into proteins, et cetera, but throughout time, even though that's still true and it's pretty rock solid and it happens, other things were found to call into question the robustness of that theory, right? Like retroviruses and things like that, okay? But so basically, any theory you see is not going to be an absolute fact. Even gravity, right? For another example, everyone loves gravity and they love physics and stuff like that, but then Einstein comes along and Stephen Hawking, and they have things like black holes where the laws of physics break down in certain circumstances. So the theory may work 95% of the time, but there's instances where the theory doesn't work. And so that's another important thing to note about the scientific method and theories, okay? So anytime you have a theory, big picture, not going to be an absolute fact, okay, in the context of the scientific method. It's basically something that you put out that you're waiting for someone to have either an exception to or prove wrong. All right, so our last question in this segment, 1-4. In the context of the scientific method, comment on the statement, no two snowflakes are alike. And we can actually rephrase this based on theories and scientific methods and things like that to be, no two snowflakes have been identified to be the same. So that touches back on the last question, 1.3, right? Is that your theory is only as good as it is until somebody disproves it. So if you say no two snowflakes are alike, what you're really saying, and this is what this question is getting at, is that it hasn't been shown yet that two snowflakes are identical. So again, very similar statement. This concludes this section of the chapter. The next section of the chapter, we're going to be looking at scientific notation and things like that. It's going to be much less abstract. But again, this is a good way to kind of show you how the scientific method works out, what the thought process is between science and publishing paper and asking questions and things like that. And it's always, always, always a great idea to start with the hypothesis and then go from there to develop a theory and things like that. So now we're heading into chapter 1, the section based on scientific notation. So stay tuned for that. That's the next video in the series.